Recording in progress.
Chalo, cams on everyone. Let's start off. The last thing we finished with modern physics, so hope everyone has started solving it. So we'll be starting with semiconductors. Like I said, we have semiconductors, bar magnets, magnetic materials, optical instruments, diffraction, polarization, EM waves. We will finish all this in the next 2 to 3 weeks. And I hope everyone has seen the revision schedule. Starting from number 17, we have around 25 sessions. We'll have speed tests and everything. After that, again, after your board exams, we'll start the advanced revision. So there are 2 revisions actually. This thing, what we're doing is specifically more for means. And after this, we'll have 1 more revision. Anyway, so these chapters, what we're doing now, are there for specifically for mains, except that Wernicke caliper screw gauze. It is only for mains. Semiconductors is not there for advanced. Bar magnets are not there for advanced. Diffraction, polarization, EM waves, all this stuff is not there for advanced. So, but better to know because I can always put a paragraph in the last few stuff. Can't argue actually. Okay. So for these chapters, right, they have almost 10% weightage in mains. That means almost you can expect around 3 questions at a mains level. Other exams, they might be there. NCERT mate is there, so it is there. Speed test will be in the class. I'll give you the paper. I'll be monitoring you. You will be writing in the class in front of me. So don't worry about that. When it starts, I'll tell you. It feels good when you correct your own paper and you find mistakes. It pinches you more. You learn faster. Anyways, so today we'll be starting with semiconductors. So let's start off with something more interesting thing, and then we'll go for more theory parts. The first thing is the logic gates. If you are doing CS, you must have seen something of this. Even if you're not, let's do it anyways. So in binary, so when you write the binary code, right, we say zeros and ones. You need to understand one thing here. When you say 0, it represents off. That means there is no voltage across the output. So you need to understand one thing. Systems have only 2 states, on and off. Either it is on or it is off. So what we did for our convenience, we converted this into zeros and ones. So whenever you hear the word 0, again, remember, this is not your mathematical 0. So when you say the output is 0, it implies the system is off. When you say the system is on, there is a voltage across the output. So let's say if there's a bulb and if it is glowing, it is on. If the bulb is not glowing, it is off. So if you apply 5 volt across the bulb, it glows. If you apply 20 volt, it glows 4 times more. I don't care. It is still 1 only. Okay, don't say it is 4 times 1 because it is glowing 4 times brighter. There's nothing like that. So that's the reason we call it binary code. So this is what people are actually trying to do, you know. Tomorrow, if you can create a system where you have 3 states. Now, we don't know how is the third state will be. Something like on, off, and some other state, I don't know what is that. Again, imaginary thing. Then you will have a 3 system code. You can actually store more data. Your system will be much faster. So when you think about quantum computers, right, and in quantum states, you can have multiple states. So that is the reason quantum computers are much faster. They can process much more data. So far hypothetical though, but now in this we have our gates. The first gate is your AND gate. The terminologies and the symbols and the things you should remember. So what is an AND gate? The symbol looks like this. It looks like a D. So you are giving A and B as an input. I'll tell you what it means. The output is represented as A dot B. So A and B are input terminals. So what is exactly AND gate? Remember this analogy, it will help you. Imagine we have a circuit with two switches, switch A, switch B. We have a battery, and this is connected to a bulb. So whenever the switch is closed, we call it as 1. If the switch is open, we say it is 0. So 0 represents which is open, 1 represents which is closed. Okay? Now, A, B, the output is A dot B. In Max, you must study it through tables. So this is how you read this. 0, 0 means what? Both the switches are open. Will the bulb glow? No. So 0. 0, 1, meaning A is open, B is closed. Will the bulb glow? No. 0. 1, 0. Will the bulb glow? 1, 1. Bulb will glow. So an AND gate is simply two switches in series. That is a simple analogy. Are you getting it? So if you want the bulb to glow, you have to make sure both the switches are closed. Even if one switch is open, which is a 0 in this case, the bulb is not glowing. So here 0 and 1 represents on and off. Switch is closed, switch is open. I clear with this thing. So these are not numbers. Understand that 0 and 1 are states. Mathematically, we're representing with 0 and 1. And the output ka symbol is A dot B. Remember, this is not dot product. This is not multiplication. Whenever you hear the word A dot B in logic gates, the dot represents you're using an AND gate. Clear with this? That's your AND gate. The second gate is an OR gate. The symbol looks like this. The output is given by A plus B. So how to imagine this? You can put two switches in parallel. This is A and this is B. So A, B, A plus B is your output. Again, 0, 0. Both the switches are open. Will the bulb glow? No. 0, 1. Meaning you're closing B, but A is open. Then what will happen? The current will flow through B, right? When you're keeping them in parallel, even if one switch is closed, the circuit is on. So 0, 1 is 1. 1, 0 is 1. 1, 1 is also 1. Are you clear with this? So again, be careful. 1 plus 1, don't say it is 2. The way to read this thing is 1 plus 1 is OR gate, both the inputs are on. So you will get on. So 1 plus 1 is 1. Are you clear with this? So here 1 is not a number, plus is not an additional sign. Plus is simply indicated as an OR gate. I hope that is clear. So there's nothing called 1 plus 1 is 2 and all. 1 plus 1 is 1 only. It is on plus on is on. Then we have a NOT gate. So NOT gate, the symbol like this, a triangle with a dot in front of it. If you have A, we get an A bar. So A bar is nothing but negation of A. This you can create using, transistors, but it is removed in the portion, so don't worry. So if you have A bar, meaning if you give A is 0, A bar is 1. If A is 1, this is 0. You always get the opposite value of it. Clear with these three gates. AND gate, OR gate, NOT gate. Yeah. The next thing, NAND gate. A NAND gate is simply if you take an AND and if you put a not in front of it, so basically you'll get A dot B ka negation. So we simply represent this with an AND gate with a circle in front of it. If you just put a circle in front of an AND gate, look at the AND gate. It is simply a D ka symbol. NAND gate, there's a circle in front of the D ka symbol. So if you just put that circle in front of it, it is an NAND gate. A dot B whole bar. So A, B, A dot B. The final output is A dot B ka bar. So 0, 0, 0, 1, 1, 0, 1, 1. This will be 0, 0, 0, 1. So A dot B ka negation 1, 0, 0, 0. Clear with that? Then we have NOR gate. So the moment you put that N in front of it, it is a negation basically. A NOR gate will have the same symbol as OR gate, but a circle in front of it. So the moment you put a circle in front of it, it becomes the negation. So what is OR gate? A plus B. A plus B ka negation is A plus B whole bar. So A plus B, A plus B ka bar. So 0, 0, 0, 1, 1, 0, 1, 1. This negation will be 1, 0, 0. Wait, I wrote something wrong. 1, 1, 0. Yeah, I wrote that thing wrong. Clear with this? Now here, theoretical question. This NAND gate and NOR gate are called universal gates. This will be mostly a theoretical question. The reason, basically the meaning of universal gates is, so when you look at your phone, when you look at your laptop or anything, when you actually break it down and you look at the gates that you're using, you'll observe no one manufactures AND gate and OR gate. Everyone, all manufacturing devices, right? Everything is manufactured from NAND and NOR gate. That's why they're called universal gates. So all circuits or all processors or whatever you want to make are made from NAND gates and NOR gates. Reason, again, the reason is in transistors, but I give the reason. Transistors removed from the portion using these gates. In transistors, right, we will see later on there's something called PNP transistors and NPN transistors. We don't have in the portion. So NPN transistor, meaning the N indicates the electrons are the majority charge carriers. So electrons will move more. In PNP, holes will move more. So the reason goes like this. The electrons move faster. Then holes. We will talk about this later on. Holes are simply absence of electrons. But CET में transistors are there. Boards में तो है. So you will need that reasoning. NPN transistors are faster than PNP. So if you use NPN transistors, you will get NAND gate and NOR gate. If you use PNP transistors, you will get OR gate and an AND gate. So if you actually think about this, in a NAND gate, there are two operations, right? But the electrons move so faster, the NAND gate works faster than AND gate. So if anyone wants to manufacture an AND gate, they will take a NAND gate and then they'll make it an AND gate. So you go reverse, faster than PNP transistors. I'll try to give an idea in the next class what is an PNP NPN transistor. Basic idea you can have. But just remember that reason and everything. A direct CET level question. Which of the following gates are called, universal gates? So they'll give you 4 options. NAND and NOR gate. Clear with this. Then we have something called XOR gate. XOR gate. XOR gate is a gate which is used to store the bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if you have a bit, you have a bit. So if I'll show you how you'll get these things. So this thing will have a double thing. So if you have A and B, the output will be A dot B bar plus A bar dot B. You can't simplify this further. It's a pretty interesting output. If you take X NOR, you put a circle in front of it. Basically, this is XOR gate का negation. A dot B bar plus A bar dot B का bar. So if you have A, B, if you have XOR, A dot B bar plus A bar dot B. If you have XNOR, 0, 0, 0, 1, 1, 0, 1, 1. So look at this XOR gate. When both are off, it doesn't work. When this is on, it works. When it works, it doesn't work. Meaning XOR gate will work only when one of them is on. Example, did you ever use a two-way switch in your house? When you're entering the room, you switch on the light. Once you go to the bed, you switch. When you switch on that again, the whole light goes off, isn't it? So your two-way switch which you used in the house is actually an XOR gate. Never used it? Ever seen a two-way switch? If you switch off both of them, it won't work. If you switch on both of them, it won't work. They will work only when one is on and one is off. You must have one in the house, isn't it? When you're entering the room, normally, think about this. When you enter the room is dark, so you want the light to switch on. You went to the bed and you're sleeping. Will you again go there, switch off, and then come back? Bad idea, right? So you keep one more switch here. And both the switches are connected. This is an XOR gate, basically. This is A and this is B. So when you enter the room, both are off, 0, 0. So light is not glowing. When you enter the room, you make it on. Light will glow. When you go to the bed, you make this also on. Then the light will switch off. Seen this thing, right? Two-way switch. That's your XOR gate, basically. Think about this. It's pretty inefficient, isn't it? When I used to stay in the old house, right? Like when I was a kid, switches used to be like that only. When you enter the room, you switch on the light. Then when you're about to sleep, you go to the thing, switch off the light, run fast and jump onto the bed again because you're scared there is a ghost. Never did that. Suppose you have to go and switch off the door, let's say kitchen is there, bedroom is there, hall is there and everything. You go to the kitchen, switch off the light and you run, you run non-stop, switching off everything and you're running as if something is chasing you. So XNOR will be negation of this 1, 0, 0 and 1. Clear with this thing. These are the 7 gates. AND gate, OR gate, NOT gate, NAND, NOR, XOR, XNOR. Clear with this. And then why is there an empty space here? No, there are some important theorems or results actually. What is A dot 0? So this is how you read it up. A dot 0 means you have an AND gate. In that one input is A and one input is 0 off. So in an AND gate, if one switch is always off, then the output is always off. So A dot 0 is always 0. What about A dot 1? So dot meaning again AND gate, one switch is always on. So if A is 0, output is 0. If A is 1, output is 1. That means A dot 1 is A only. A dot A is A only. A dot A bar, meaning if this is 0, that is 1. If this is 1, this is 0. Means it is always 0, isn't it? If one is open, the other is closed. The other is open. This is closed. Similarly, A plus 0, A plus 1, A plus A plus A bar. What do you guys think? Again, plus meaning OR gate. A plus 0. So in an OR gate, one switch is always open. So that is A. If this is 0, 0. If this is 1, it is 1. So A plus 0 is A. A plus 1. OR gate mein one switch is always closed. Means it will be always on. A plus A is A. A plus A bar is 1. Sure with this? Again, don't try to remember them. Understand the meaning of it. The plus meaning OR gate. A plus A bar means one switch is closed, the other is open. So it will be always on. A plus B is same as B plus A. So if you have A dot B plus C, this will be A dot B plus A dot C. 11th and 12th are the most important ones. This is the De Morgan's theorem. A plus B whole bar becomes A bar dot B bar. So if you want to split the negation, the plus becomes dot. Similarly, if you have A dot B ka whole bar, if you want to open the negation, it becomes A bar plus B bar. You should definitely mug up these two. Should remember them. You can write it down if you need. We are going to do problems based on this. There, if you know these things, it becomes pretty easy to solve circuits. So let me show you some questions how they'll ask. And logic gates are important. I think last year, out of that 14 or 12 papers, almost in 8 papers, there was a logic gate questions. One question. Any doubts on this page? Let's see a few questions. So this is A, this is B. That's an AND gate, that is an OR gate. What is the output? So exam options will be the output is an AND gate, output is an OR gate, output is A, output is B, output. They'll ask you something of that sort. Options will be like that. How do we solve this? Take a minute, then I'll show you. Some people try to use that, truth table and all. Don't do that because it is easy. If you have four logic gates, you will go mad. I think for 10-15 seconds, I'll show you one. Question way of this sort. This is the gate, and how will it be? Listen, I'll show you one. So you're giving A and B. So this is an AND gate. Let this be A dot B. For simplicity, let's call it C. This is B. So this is also B. So for an OR gate, you are giving C and B. Agreed? So this is your OR gate. So the output will be C dot B. So your output is C dot B. But what is C? C is A dot B. Sorry, C plus B. C is A dot B plus B. So I can write this thing as A dot B plus 1 dot B because 1 dot B is B only. Then this will become A plus 1 dot B. A plus 1 is 1 only. And 1 dot B is B. That means for this circuit, the answer is always B only. Whatever is B ka input, the output will be the same. It doesn't matter on A ka value. Are you clear how we solve this? Using truth table is one way, but that becomes lengthy. So this is how you need to simplify. And that's the reason you need this page. Clear how we simplified it? Let me give you one more now. You guys try. But any doubts on the first question, please ask. What is the output for this? OR gate, AND gate, then both are connected to a NAND gate. A plus 1 is 1 only, na? For an OR gate, see A plus 1, plus meaning OR gate, you give 1, so it will become 1. So 1 dot B is B only. Yeah? Yeah. Here, A plus 1 is 1. So for an OR gate, if you give input as 1, it is always 1. How do we do this? Try, take a minute. That's it. If you got the hang of this logic, there's nothing more. You'll get it. And I'll send you a few questions after that, with the notes. Especially if you do the PYQs, it is sufficient. So I'll send you a small list of PYQs of 2021, 22, 23. You can do your PYQ book also. Second and third period. What kind of answer is that, Raditya? A bar plus B bar. What gate is that, Rehan? Zero near a See? So you're giving A here, you're giving B here. This is an OR gate, so you get A plus B. For convenience, let's call it C. You're giving B here, you're giving D, A here. This is A dot B. Let's call this D for convenience. So this is a NAND gate. So this is C dot D ka bar. Agreed. What is C? C is A plus B. What is D? D is A dot B ka whole bar. So let's expand it inside only. This will become A dot B plus B dot A dot B ka bar. This can be written as A dot A dot B plus B dot B dot A. We know A dot A is A, B dot B is B. A dot B plus A dot B, don't say 2 times, it is A dot B only. What is A dot B? AND gate. What is the bar of this? This is a NAND gate. So this whole thing can be replaced with a NAND gate, and that would be the answer. Okay, well, this option should be like that. Is this an AND gate, NOR gate, or answer is B, or answer is A, something of that sort. 3 cases we get once, one. I don't understand that, but doubt is clear na, Aditya? No? Just unmute and ask na. Doubt is clear na? Haan, theek hai. It's an AND gate. All got this? Any doubts on how I expanded the whole thing? It'll take little practice, not tough. You get used to this. Because this is what will happen. If you start putting 3, 4 gates, you will start going mad actually if you use truth tables. Let's see one more. Hmm. What is the output of this guy? Hmm. These are four NOR gates. This fourth question is actually a JEE mains ka PYQ. Right, Aditya. Try. Here, truth tables will make you go mad. Right, Ansh. Right, Vignajit. Third looks complex, but if you know what result is that, it is easy. Yeah, right, Most of you got it. Get the fourth one also. Think, I'll give you a minute, then I'll show you three and four. Let's see. Now, look at this one. This is A. This not get made it B bar. So you are giving A bar, A and B bar to the AND gate. So this guy is A dot B bar. This is B and this is A bar. So this guy you're giving A bar dot B and then you're adding them. So that is A dot B bar plus A bar dot B bar. This is XOR gate ka output, na? You cannot simplify it further. That's what I said. You should know how an XOR out gate output looks. If you start using truth tables or if you try to figure it out, you can't simplify it further. That's an XOR gate. There, that is how you construct an XOR gate. Two-way switch. What about the fourth one? Try fourth one. Right, Devansh. Near Shana. Fourth one, be careful. It looks complex, but that was actually a JE question. One, mere. You're saying it'll be always on. Do it aram se. It can be confusing because of that dot, na, everything becomes negation. नहीं बोल बजा नहीं रे Shall I tell you the answer? You'll get X XNOR. Now figure out how you're getting X XNOR. Try. I'll give you a minute. XOR का negation था ये. Don't worry about these things. If you do some 10 questions, you'll get the hang of all these things. They're pretty easy after that. These will be the toughest ones. Show you one. See, this is A. This is A plus B ka whole bar. This is B. So this guy is A plus B ka whole bar ka whole bar. Agreed. Let's expand this. How to open A plus B whole bar? A bar dot A plus B whole bar ka bar. De Morgan's theorem, isn't it? A plus B ka whole bar is what? A bar dot B bar. Plus becomes a dot and you get a negation on both of them. So this will be A bar dot, what is bar bar? It becomes A plus B only. The two negations goes off. This will be A bar dot A plus A bar dot B. What is A bar dot A? 0. So this is simply A bar dot B. Similarly here, this guy will be B plus A plus B ka whole bar ka bar. You solve this, you'll end up with A dot B bar. So you are giving A plus B and A dot B to this guy. So this is A bar dot B plus A dot B bar to an OR gate, but it is a NOR gate, the overall negation. This is XNOR. Clear? Understood your mistake? Check it out. Take your time. Take your 30, 40 seconds. Have a look at this. Ask me if you're confused anywhere. So how you expand this and everything, it's important. You could have actually simplified inside and then expanded. Then how will that look? A plus B whole bar. If I try to first open the negation inside, A plus, this will be A bar dot B bar. Then I can't take out anything common there actually. I have to open it now. If I open this now, this will be A bar dot B bar ka whole bar. This will be A bar dot, and that will be A bar bar plus B bar bar, which is yeah, same as this guy again, isn't it? कुछ भी करो तो you'll get that only. Doesn't matter how you play around. It's a complex one, easy nahi hai, but should have done few models like this. Clear this. If you can get 3 and 4, I think you got the main thing. You'll be able to handle most of it. Now, other than this, sometimes they'll play like this. You have a 3 input AND gate. Most people will see and get psyched. Forget about how many inputs are there. What is an AND gate? Switches in series, isn't it? If you have 3 inputs, meaning what? There are 3 switches in series, isn't it? That's it. Whenever you think of an AND gate, think of that analogy of switches in series. OR gate means switches in parallel. That will make your life easy. Let him give 10 inputs. So you will find 3 input ka this thing also. What is the final output? It's a 3 input AND gate and an OR gate. So there is nothing like there should be always 2 inputs. They can play around like this with 3 input terminals. NAND gate नहीं रे, और gate of B नहीं. Let's see. So this guy is a AND gate. So A dot B dot C. The moment you put a word dot, it is an AND gate. So you're giving this, and this is C, and this is B bar. So you're giving A dot B dot C plus C plus B bar or gate, na? So plus signs. Clear how to write the output for a 3 terminals? A dot B, it is A dot B dot C. So take out C common here. This will be A dot B dot C plus 1 dot C plus B bar. If you take out C common, it will be A dot B plus 1 dot C plus B bar. A dot B plus 1 is 1. Anything plus 1 is 1 only, isn't it? The OR gate plus 1 is 1 plus B bar. 1 dot C is C, so it is C plus B bar. That's your answer. So options would be something like this. The output is independent of A, output depends on A, output does not depend on B. There'll be options of that sort. So if you see this thing, right, it doesn't matter what is the value of A. The answer only depends on B and C. Clear how to handle this thing? The operations will still work. You can just always separate out. You can do all those things that you know shown in this page. Clear with the gates, everyone. Not tough. All you need is some practice. Right? 10-15 questions, that should be enough. You will get the hang of it. Great. So that is a bit about the gate. So next thing. So now we got a lot of theory. So listen carefully. So we want to create zeros and ones. That is on and off. That is a whole story, right? So whatever you're doing is to go to that point of the story there. So that means we need a material where when you give a little voltage, it should become on. When I don't give voltage, it should become off, isn't it? So we are searching for a material like that. And we know there are 3 materials. There's an insulator, there is a conductor, and there's a semiconductor. And if you take an insulator, no matter how much voltage you give, current will never pass. Means an insulator is something which is always off state. If you take a conductor, it is always on only. Matlab, a little voltage current will start flowing. It is always conducting. But if you look at a semiconductor, right, it is in between them. Means by doing something, it suddenly becomes like a conductor. If I don't do anything, it behaves like an insulator. So semiconductor is a very proper material for this kind of a thing. That is the reason we call it semiconductors. So how do we define what is a semiconductor, what is an insulator, what is a conductor? We have to start from the basics. Consider if you have only one atom. We have done this in Bohr's theory. What is the energy of an orbit? Minus kz square by 2r. Remember? The total kinetic energy, total energy of an orbit is minus k q1 q2 by 2r. Gravitation means minus g m1 m2 by 2r. So energy is proportional to 1 by r. So if you try to draw the graph, this is what you get. This is a hyperbola, rectangular hyperbola. E into r is constant. And if you look at the orbits here, we have 1s, 2s, 2p, 3s. So the first orbit will have more negative energy. As you go higher, the energy gets closer to 0, but the energy is all negative. All great. This is what happens if you have one atom. But when you take a lattice, you have hundreds of atoms. Now, when you have hundreds of atoms, what will happen? That electrons are not under the influence of only one nucleus, but they're under the influence of multiple nucleus. So this is what something like would happen. So if this is a nucleus, let's say there's one more nucleus here. So if you look at this electron in the outermost orbit, right, it is going in a circle. Then when it, because the orbits are overlapping, it will jump into the other orbit. Then it can jump into the lower orbit. It can jump here. It can jump here. You can see what is happening. Because the atoms are overlapping here, this electron which is going here will be under the influence of the other nucleus also. Sometimes they'll jump like this. It'll jump here. Then it'll go here. Then it'll jump here. It can jump here. This electron can just move around anywhere it wants. These electrons are called free electrons. These are the electrons which are responsible for conduction in current, electricity, or heat transfer. Now, if you look at, there are another electrons which are sitting inside the orbit, isn't it? If you notice, there are electrons sitting in this 1s orbit. Do you think these electrons can jump and move around? Because for these electrons to jump, they need some energy to reach the outermost orbit, isn't it? So all electrons in a conductor or in a metal, right, do not participate in this conduction. So only the electrons which are in the most outermost orbit, which are overlapping, they will be responsible for this motion. So electrons in the overlapping orbits can freely move across the lattice. These are called free electrons or conduction electrons. And the electrons in the other orbits are not free to move, are called valence electrons. Again, terminology is important, everyone. You should know what is a conduction electron, what is a valence electron. So now if you have multiple atoms like this, now if I try to draw the energy level for all the atoms, you will notice, there is one common energy level. So the same example which I gave you. So in this scenario, if you look at this, this is 1s, this is 2s and 2p, and this is your 3s. So what is a common energy level? 3s orbit, right? That means any electron in 3s or beyond, they are free to move from one nucleus to another nucleus. They can jump around. So to give an analogy like this now, when I was a kid, right, our society ka houses used to be like this. Everything used to be like 2 to 3 floors ka apartments, small buildings. And there used to be very small gap between the houses. So when we used to play hide and seek, we used to jump over the buildings and we used to hide anywhere. You must have seen these buildings like this in Mumbai also. If you see these SRA ka buildings now, the people that build this building, 10 floors ka buildings, and you'll find a cluster of them. You'll find like 20 buildings or 15 buildings. And if you see now, the terraces are connected. You can actually jump from one terrace to another terrace. Ever seen that anywhere? Or did that anytime? So when I was a kid, we used to play like that hide and seek. You're getting into one house and you're coming out of another house. And nowadays the people will be to right and left, but that time it was fine. Like everyone knows everyone in the society, right? So think of like this. So you have constructed buildings. Let's say we have 10-floor buildings. And all these 10-floor buildings, right, are connected with on the terrace, they're connected by a platform or a bridge. Now think about this. Any person who reaches the 10th floor, this person can freely move from one building to another building, isn't it? That is your free electron. Any person, let's say, who's in the 6th floor, can he jump from 6th floor to 6th floor? You can't do that. So you're stuck here. Getting it? You cannot participate in any motion or anything. If you want to participate in conduction, first you need to go from 6th floor to 10th floor, then you can move around, isn't it? So these electrons which are stuck here are called valence electrons, and these electrons which are moving here are called conduction electrons. Is that making sense? Kind of like that. That is the analogy there. And we define, so this common energy level. So the first time, let's say after this, the building, right, becomes like this. After the 10th floor, the building is actually becomes a big block like this. Seen any building like this anywhere? Singapore, Marina Base. Can you see that building? You have 3 towers, and the top there is a ship. Didn't see the building? When you at least photo तो देखा होगा ना? You should check it out. The Singapore का the Marina Base, I guess, the name of that building. You have a ship on top of that 3 buildings actually. So once you reach this level, right? So this is the story there. So this is your common energy level. Anyone who reaches this level is free to move across anywhere, isn't it? So this is called conduction band. So conduction band is the energy level, which is the common energy level for the electrons. Then we define something called a valency band. What is a valency band? Valency band is the highest energy of energy, highest level occupied by the electrons. Let's say in that building, people are only there till 6th floor. So what is the highest occupied level? 6th floor. What is the common energy level? 10th floor. That is your conduction band. Let's say if you take an element like magnesium or something, it's a good conductor. The electrons are filled till 13th floor. What is the valency band now? 13th floor. The highest level occupied by the electrons is called valency bands. It has nothing to do with your conduction band. What is a conduction band? The common energy level where the electrons are free to move is called the conduction band. Are you getting the two definitions, everyone? So energy levels above the common energy level is called conduction band. Valency band is the highest energy level occupied by the electrons. Both of them are independent of each other. Any doubt so far? You're getting the story there. So in this case, if you see this green line which I'm drawing here is your common energy level. Any orbit beyond that green line, the common energy level, is in a conduction band. These electrons are free to jump around. It's like your buildings are connected to the 10th floor. Anyone who's living more than 10th floor and higher, you're free to move. So you all are in the conduction band. Anyone below that, let's say, but the building is occupied only till the 6th floor. That's your valency band. Clear with this? Then here we also define something called a Fermi level. So again, another important thing. But remember, you will hear these words and you'll not understand what is Fermi level and everything. Valency band, conduction band, Fermi level. So Fermi level is again nothing new. At 0 Kelvin, the highest energy level occupied by electrons is called Fermi level. Basically, valency band at 0 Kelvin is called Fermi level. So technically, there is no difference between valency band and conduction band. At 0 Kelvin, we call valency band as Fermi level. Example, suppose let's say you have a nucleus. And let's say we have electron here, electron here, electron here, electron, electron. Let's say it's a carbon atom. So at 0 Kelvin, if someone asks you what is your valency band here, you will say 2p. And someone asks you what is the Fermi level, you will also say 2p, 2p or 2s, whatever it is. But same thing, let's say if you have temperature, let's say 300 Kelvin. Now, because of this thermal kinetic energy, one electron has jumped into the higher orbit. We saw in atomic collisions, if you give temperature, the atoms will collide and electrons get excited. Again, just to give an example, let's say electron excited to higher orbit. Due to thermal energy. 3/2 kT, hope you remember. Thermal kinetic energy. Now, if I ask you what is your valency band, the highest energy level occupied by the electrons, 3s. What about the Fermi level? Fermi level is undefined. So Fermi level is defined only at 0 Kelvin. If you increase the temperature, there's nothing called Fermi level. Clear with this? Yeah. So there. So far, what are the new terminologies? Conduction band, valency band, Fermi level. Conduction electrons or free electrons, valence electrons. So total, there are 5 terms. All are related. So an electron, which is with single atom, and electron in a lattice, they behave little differently. The electron in a lattice can freely jump from one atom to another atom. So they will tend to behave in a different way. Clear with this? So instead of having the electron, instead of saying the electron has a specific orbit, now suddenly it actually expands. It can occupy more levels. That 2s does not look like a single layer, but 2s will actually spread out. You can be in a more bigger region. Just for an example, suppose if I take a carbon atom, 1s, 2s, and 2p2. Now look at this thing. So when, again, just an approximate diagram, if you have two carbon atoms, if you look at this, what is the common energy level? 3s, na? So if you take a carbon and carbon, the 3s orbit is overlapping. But where are the electrons present? Up to 2p only. So valency band is 2p, conduction band is 3s. There are no electrons in 3s. So that is the reason carbon is not a good conductor. If you take pure carbon, it does not conduct electricity. Graphite is a special case. Hope you know why. Graphite is different. It's an exception. Because of the layers between them, you get some free electrons and all that stuff. And that's the reason graphite slides easily also. It's a good lubricant. Right? And where else we use graphite? We saw recently in a nuclear reactor. Where? Options will be like, is it a coolant? Is it a control rod? Is it in a moderator? Is it in a क्या था दूसरा? Fuel rod or something like that. What rod? Control rod nahi radiator. Moderator it is. Control rod is what? Cadmium boron rod. It absorbs neutrons. Graphite, what does it do? When the fast moving neutrons collide with the moderator, they slow down. You wanted a slow moving neutrons. Don't forget. Graphite is used as a moderator. And what is a moderator? It slows down the neutrons so that they can be absorbed by the uranium. Now look at sodium. Sodium is a conductor. 1s, 2s, 2p6, 3s, 1. Now if you look at this, there's one electron sitting in the 3s orbit. Now. These things are free to move. So here the valency band and the conduction band is 3s. There are free electrons. That's why sodium is a good conductor. Sodium is a metal. And we use sodium in coolant. Sodium can easily remove the heat from inside and bring it out. So we use it as a coolant in a nuclear reactor. Cool gaya na sab? The liquid sodium is the best coolant. Graphite is a moderator. Questions ऐसे ही आएगा, huh? One question and then you will mess it up and then come and then you'll cry, oh shit, such a easy question kar. Clear with this? I hope everyone is getting what is the valency band, what is the conduction band. So now if you take an insulator, the gap between the conduction band and the valency band is high. So in that building example, conduction band is the 10th floor, valency band is in the 5th floor. So for people in the 5th floor to go to the 10th floor, you need to give a lot of energy. In case of a semiconductor, the conduction band and the valence band, the gap is very small. Again, just to say what is a conduction band, the common energy level. This is the energy level, or this is the point where the buildings will start converging. What is the valency band? The highest energy level occupied by electrons. So in case of a semiconductor, the energy gap is less than 3 eV. In case of a conductor, the bands are completely overlapping, so you have a lot of free electrons. You need not do anything. So the reason why we like semiconductors is because of this. If I give a little voltage like 1 or 2 volts, electrons will start jumping, it becomes a conductor. If I don't give voltage, electrons will not jump, it becomes an insulator. So you have created on and off, isn't it? That is the reason we use semiconductors to make chips, not potato chips, electronic circuit chips and all that stuff. Clear with this? There. So all the story that I told you is to establish a fact why we need semiconductors. Why can't we make chips with conductors or insulators? And how do you even define a semiconductor? So semiconductor is simply defined as any material whose energy difference between conduction band and valence band is less than 3 eV. Clear with this? So far clear? So definitely you guys should maybe, tomorrow before sleeping or maybe today also, at least tomorrow you should revise the whole theory once. You should just give a reading once. I'll be sending you some reading material also on this. Take a small break, come back by 9:37. We'll continue from here. We got more theory after this. Any doubts so far? Chalo, come back in 5 minutes. Chal, let's start off. So we are clear. Semiconductors are the ones we want to use to make logic gates. Then with semiconductor, so we need something which is cheaper. That is always the first option, right? We need something to be cheap, and when it is cheap, it is abundant and easy to process and everything. So we generally prefer silicon because silicon is abundant. Germanium is even better, but problem is germanium is not that available. It is expensive. So that is actually one of the problems we are facing with solar panels. Most of solar panels we make it with silicon, and silicon solar panels have like pretty less efficiency. Like they'll give you around only 4 to 5% of it gets converted into energy. If it's a germanium solar panels, we can get actually 3 to 4 times more electricity. It actually would have been more profitable, but we don't have germanium is too expensive. So we use pure semiconductors without any impurities. These are called intrinsic semiconductors. Again, terminology is important. So if you take pure semiconductors like silicon or germanium, these are called intrinsic semiconductors. Now, if you look at silicon, silicon has 4 atoms in the outermost orbit. So it will try to form an octet configuration with another 4 silicon atoms. Now, so each one will contribute one electron. Everything is great. Silicon is pretty nice, stable and all. It gets a good octet configuration. So at 0 Kelvin, there are no free electrons. Everyone is happy sitting inside their orbits. But once you start increasing the temperature, kinetic energy 3/2 kT, the molecules will start vibrating, all that stuff. Electrons will start getting out of the orbits. Some electrons will jump from the valency band to the conduction band. Again, think of like this. What is a valency band? The highest energy level occupied by the electrons. What is the conduction band? The common energy level. So electrons will jump from the lower orbits to higher orbits, which is valency band to the conduction band. Now, whenever the electrons jump from there, you will get a vacancy there. These vacancies are called holes. So hole is actually an imaginary particle. It doesn't exist. Hole is just your imagination. It's an absence of an electron is called a hole. But the way it behaves, right? It behaves like a positive charge. Think of like this. Let's say if you're sitting in a class and let's say there's a person here, there is a person here, there is a person here, and there is a vacancy here. So when this person goes here, vacancy will come here. When this person goes here, vacancy will come here. When this person goes here, vacancy will come here. So for a person who is just looking at the vacancy, how does it feel? It feels as if this hole is moving, right? And if you actually think about this, how did we define current? Current is the flow of positive charge. Tell me one thing, does positive charge ever flow? It is actually the movement of electrons, isn't it? So here it gives you a feeling as if the hole is moving. Whereas in reality, the hole is nothing but electrons which are coming back. It feels the hole is gap is going forward. Making sense. So we call this thing holes. They behave like positive charged particles, but technically they're not. Now tell me one thing, which is faster? The people jumping from one vacancy to another vacancy, or this guy simply coming and walking here? The guy who comes and walks directly will reach faster, isn't it? So electrons move faster than the holes. Getting it? So conduction electrons, right, which are moving in the lattice, they actually carry the current much higher compared to these holes which are jumping inside one after another. There is always a delay. So the holes are nothing but the absence of electrons. They behave like positive charges. Here, these are the free electrons move in conduction band, whereas the holes move in the valency band. So this is what is actually happening there. So we have the silicon, we have electron, we have electron, we have a hole, we have electron, electron, electron. So this electron will jump here, we get a hole here. This electron will jump here, we'll get a hole here. So for a person seeing this, will feel like as if the hole is moving, whereas in reality, electrons are jumping everywhere. Clear with that? Now here we have few terminologies there. So we define something called mobility. Mobility is drift velocity per unit electric field. Everyone remembers drift velocity? ये formula याद है? I is equal to NEA V drift. Comes from current electricity. V drift. Remember now what is V drift? The electrons moving in a conductor have two different velocities. Remember? Thermal velocity and systematic velocity. The thermal velocity, you're just moving random. This will never create current. The drift velocity is a slow velocity which is coming due to the electric field or something that will create the current actually. So mobility is defined as drift velocity per unit electric field. The mobility of electrons is more than holes. So electrons move faster than holes. It's almost 10 times higher. That is the reason if you construct an AND gate, it works because of movement of holes. If you construct a NAND gate, it works because of electrons. That's why NAND gates are faster than AND gates. That's why I told you there, PNP and NPN transistor करके. So an intrinsic semiconductor, the number of electrons per unit volume is equal to number of holes per unit volume, because for every one electron that jumps, you get one hole, isn't it? The electrons and the holes will have same concentration. This is important law of mass action. And this is a theory which you should remember. This can be even a HSC board question. Define law of mass action. So what this thing says is the product of number of electrons per unit volume into number of holes per unit volume. The product is always constant, Ni square, where Ni is called intrinsic concentration. That is the number of total charge particles per unit volume. This is your energy gap. So this Ni depends on temperature. Higher the temperature, more electrons will come out, so you get more holes. So this is one formula which you need to mug up. The law of mass action. There have been questions on this. So no matter what you do, Ne into NH the product will always remain constant. The K here is Boltzmann constant. There. So here we have two new terminologies. One is your mobility and one is the law of mass action is a formula. Clear with this? Next thing. Now you guys remember the current ka formula, I is equal to NeVd. Because in conductors, if you see, all the current is flowing because of electrons. But in a semiconductor, even holes will carry some current. So the formula changes. The current in a semiconductor is given by NeAV drift of electrons, N holes EAV drift of holes. So there's a hole current and an electron current. In case of conductors, electrons are much, much higher. So we used to neglect the hole current. So the formula will be like this. So they do ask such things. Simple questions. They'll give you the drift velocity, they'll give you Ne, they'll give you NH, they'll give you everything. They'll ask you find current. You just have to use I is equal to NeVd two times. One is for the electrons and one is for the holes. And then this thing, I'll show you the derivation for conductivity. So we got this whole current. So I is equal to Ne, E, A, V, E. NH is the number of holes per unit volume. Charge of the hole is positive charge of electron, VH. If you bring A on both the sides, I by A, remember what is current per unit area? Current density, J. Ne, A, V, E plus NH, E, VH. J is your current density. Anyone remember there's a relation J is equal to sigma E? Sigma is conductivity. 1 by sigma is resistivity, rho. So this becomes J is equal to sigma E, which is NeEVE plus NHEVH. If you divide by electric field, this will become NeEVE by electric field. NHE by VH by electric field. What is drift velocity per unit electric field? Drift velocity per unit electric field is mobility. The sigma becomes NeE mobility of electron plus NHE mobility of holes. This is the conductivity of this is the formula there. Conductivity of a semiconductor. In case of a pure conductor, this NH is almost negligible. Ne is huge value, so it won't matter. Pretty rare, but long back, 2015, 14 times they used to ask questions based on this. Recent times, not much, but we can never know. They'll always ask, and then people will say, "Oh, these things have come." Better to be careful. You mobility, law of mass action, conductivity, current in semiconductor. These are four new things. Not tough, but you should know what you're doing. I hope this you clear now how we got NEAVD. We are just adding electrons plus hole current also. That is the only new thing there. Law of mass action is completely new for you guys. Mobility is also a new terminology for you. You never heard about mobility before. But the problem with the intrinsic semiconductor, right? The electron concentration is too small. You're completely depending on temperature, isn't it? More temperature, more electrons will come. So your circuits are not really that great. So people realized if you use only pure semiconductor like silicon, they're really not that fast. Just imagine you switch on your phone and it takes 15 minutes. You'll go mad, right? Your game ka ping will be almost like 3 minutes or 4 minutes. You shoot a gun and after 4 minutes the bullet goes and hits him. So games will be horrible. There'll be too much lag. We cannot even have this class right now, isn't it? I say something and you'll hear after 2 minutes or 3 minutes. So people said these are semiconductor is good. So the whole story, if you go right, semiconductor is good, but it is not conducting enough. So we start doing something. We introduce impurities. So we introduce impurities. These are called extrinsic semiconductors. Pure semiconductors are called intrinsic semiconductors. So this process of introducing impurities is called doping. Again, a new terminology, everyone. So they'll say like this, the intrinsic semiconductor is doped with phosphorus. So you should know what is the meaning of doping. So doping is a process where we replace silicon atoms with trivalent atoms. That is called p-type semiconductor. Getting it? So if you replace atoms with trivalent atoms like gallium, we call it as a p-type semiconductor. So what we're doing here is, so we have a silicon, silicon, silicon. This is a gallium. So this silicon will try to form an octet configuration. So we get two electrons, two, two. Silicon will bring one, but gallium will not have an extra electron, isn't it? Now silicon will have an octet with only seven electrons. So you get an extra hole. So in that bonding way, you create an extra hole there. So for every one gallium atom that you keep, you get one hole, isn't it? So you are creating extra holes in the system by adding impurities. So the number of holes will be approximately equal to the number of gallium atoms. These are also called as acceptor atoms because these atoms want to take electrons. In this case, acceptor atom is a gallium. So in p-type semiconductors, what are the majority charge carriers? Holes. Means if you try to send current through this p-type semiconductor, holes will move a lot compared to the electrons. Majority charge carriers are holes. The number of holes are greater than number of electrons. But remember the law of mass action, the product of NH into Ni is always constant. So that product will remain constant. Now, one question here. What is the charge of p-type semiconductor, positive or negative? What is the charge of a p-type semiconductor? It is neutral. There's no charge. Most people, right, think like this p-type positive. We think like that. Nah, understand one thing. What are you doing exactly? You replaced a neutral silicon atom with a neutral gallium atom, isn't it? You didn't remove any electrons here. This hole was created because you didn't get a complete octet, isn't it? That's why you got a hole. But for the number of protons inside the gallium atoms is equal to number of electrons of the gallium atom. So gallium atom is still neutral. Are you getting it? You simply replaced a neutral silicon with a neutral gallium. So why will you get any charge? So the meaning of p-type is the majority charge carriers are holes. The current flows because of holes. Therefore, we call it p-type. Clear. P-type does not indicate it is positive charged. Be careful. Most people goof up. It will be a pretty good CET level question. Or even at a mains, they might ask you the statements. General misconception. People think p-type is positive. P-type semiconductors are neutral. We are replacing neutral silicon atom with a neutral gallium atom. Because the gallium has only 3 electrons, you cannot complete an octet. You get a hole there in the octet configuration. Right? And one more thing they can ask you, what happens to the Fermi level? You can ask yourself, what is Fermi level? The highest energy level occupied by electrons at 0 Kelvin. Now, when you put gallium atoms, you're getting holes here. So what will the electrons in the higher orbits do? Think of like this. You have a building. People are staying till 6th floor. Now you got vacancies in the 3rd floor and the 2nd floor. What will the people do? They'll start coming down. They'll occupy the lower orbits. So the highest level occupied with electrons will decrease. So Fermi level will get closer to the valency band. Are you getting it? The Fermi level will drop down a bit. There was a question like this in, I think, 2-3 years back, a JE question. They said when they added acceptor atoms, what happened to the Fermi level? Fermi level comes down closer to valency band or comes closer to valency band. So basically, electrons from higher orbits will come down to fill the holes in the valency band. Clear with this? These all are theoretical questions. So I'm putting down all the important theoretical stuff. So clear with this thing. This is a p-type semiconductor. Same thing I can do with an n-type semiconductor. We call it an n-type semiconductor if you introduce a pentavalent atoms like phosphorus. So if you replace silicon with phosphorus, now we have 5 electrons. So 4 will go for octet, but there is one free electron which will not participate in the octet configuration. So this guy can freely move around the lattice. So the majority charge carriers are electrons. That's why it is called an n-type semiconductor. The number of electrons is equal to number of phosphorus atoms. Electrons are greater than this thing. Fermi level goes up towards the conduction band. N-type conductors are neutral. Because now you have more electrons, you will fill up the higher orbits, isn't it? So your highest occupied level will increase. Clear with this? There. So how did we start the whole story with? We started the whole story with when you take an atom in a lattice, instead of just going around one nucleus, these electrons can freely jump from one atom to another atom. These are called free electrons. The electrons in the lower orbits are stuck there. They cannot get out. So these are called valence electrons. So this common energy level is called conduction band. The highest occupied level is called valency band. Valency band at 0 Kelvin is also called as Fermi level. Then the gap between the conduction band and the valency band is the energy gap. If the gap is small, we call it as a semiconductor. So by giving little energy, semiconductor will become like a conductor. By not giving energy, semiconductor will behave like an insulator. So basically, you created a perfect material which can be on or off. All you need is a little input, it can become on. No input, it becomes an off. Then we took a pure semiconductor, like only silicon. Then we had a problem. Pure silicon has so less conductivity. Even when it becomes on, the signal is very weak. So we are not happy with that. Then we started adding impurities. If you added trivalent atoms, you got a p-type semiconductor, which had holes as a majority charge carriers. If you added pentavalent atoms, you got extra electrons. It's an n-type semiconductor. So we have created 2 types of semiconductors, a p-type and an n-type. Clear till here. Now the game starts from here. Now once you have p-type and n-type, you can actually use this to make something. If you take a p-type and n-type, and if you try to combine them, This is how you make it. You take a pure silicon wafer. From one side, you inject p-type material like gallium. From one type, you introduce something like phosphorus, pentavalent atoms. You inject them from both the sides. So you're introducing impurities, right? If you ever heard about them, they call them fab factories. Fab factories. Heard about them? We don't have one in India. These things are very few countries in the world have it. Taiwan is the biggest manufacturer of machines which will construct chips, right? I think we have one in Singapore. So in India, right, if you construct a chip or something, if you design a chip, you can do designing in India. Then you have to send this design to Singapore. Then they will print the chip there and then bring it to India, right? And then they put a stamp made in India and then we'll show, yeah, yeah, we made it in India. Unfortunately, that is a problem. We design chips. We have that, we have the skill and the power and everything, but we don't have fab factories here. They're very expensive. Uh, you need a very good facilities. Like, it has to be, there should be no vibrations, nothing, clean rooms, very expensive, and you need a very high skilled people. India, we do manufacture up to something like 80 nanometer ka chips. This is for some defense companies and everything. You know what is 80 nanometers? The phone which you are using, right? It has 12 nanometer ka chip. Currently, right, the world is progressing towards 4 nanometers and 5 nanometers. That is the size of the chip we are fighting for. We are still at this stage of 80 nanometer. Recently, they manufactured it last month or something, 2 weeks back. Right? Our prime minister has proudly told we started chip manufacturing. 80 nanometer. Okay, at least they started something now. So unfortunately, that is a problem. And the best part is this: the company which will make the machines to make these chips is in Taiwan only. So if China wants to make, and why do you think US is protecting Taiwan so much? Have thought about it. US is not such a good person. He will go and help everyone. The moment China goes and occupies Taiwan, that entire Taiwan ka technology of making chips and everything, China will occupy. It become the entire control will go under China there. So it is protecting Taiwan and Japan and everything. So they just act like good people only when there is a need. US is always like that. They have a very clear agenda. Like in IIT, we used to have a joke. Sometimes in curry mein, the hostel mein, curry mein there used to be a lot of oil. And if someone says, "Arey, bahut, isme, there's a lot of oil," people say, "Arey, don't shout, re. If US knows there's an oil, they'll come and attack here." That was a joke during that times in 2000s. Because whichever country had a lot of oil, US used to go there. Iraq, Iran, Kuwait, literally every country US was there to attack. And every time it is because of oil. That was a joke then, but now it is different. I think whichever country can make chip manufacturing, US will be there. Anyways, so once you take this PN junction ka silicon wafer and you inject P-type and N-type, now what happens? Look at this thing. On the left-hand side, P-type, you get a lot of holes, but don't forget, there will be some electrons. Because law of mass action, number of holes into number of electrons is Ni square. You cannot eliminate all the electrons. There will be some leftovers. Similarly, on the right-hand side, you're putting an N-type, so you have a lot of electrons, but some holes. Now you tell me, if you have so many electrons and so many holes, you think electrons will keep quiet? They'll start jumping. Why? Diffusion. That is the same reason why if you spray perfume in your room, why does it spread throughout the house? Because the concentration of the molecules is so high, they will start diffusing, isn't it? So things will always try to go from high concentration to low concentration. So here electrons are there, holes are there, electrons love to go and jump into the lower orbits and they're getting a chance, so they'll not keep quiet, they'll start jumping. So due to the high concentration, due to the high concentration of electrons, they diffuse. Into p-type, so thereby neutralizing the holes. This is called, they will diffuse from n-type to p-type. This is called diffusion current. because this is happening due to diffusion. Now something happens. Now, because these things are jumping, initially it is great. Electrons are happy they're going there. But once you start jumping, this side starts becoming negative charged. And because n-type is losing electrons, it becomes positive charge. And these induced charges will start creating an electric field between them. Kind of like capacitor's story. So as the electric field is increasing, now see, as more and more electrons will jump, the electric field becomes stronger and stronger. At some point, the electric field is so strong, when the electron tries to jump, what will happen? It will be pushed back again. Electron jumps, it will be pushed back again. So here, the induced charges are fighting with this diffusion current now. Now the question will change. Huh? They'll ask like this. In a PN junction, what is the charge of MP type? In PN junction, P-type becomes negatively charged. N-type becomes positively charged. So look at the question. What is the charge of P-type semiconductor? Neutral. What is the charge of P-type in a PN junction? Negative. Are you getting it? Once I add the word PN junction, the answer changes. N-type becomes positive charged. And these charges produce an electric field which opposes this diffusion current. We get something called a drift current, because the electric field will make the electrons drift back again. So there are two things fighting now: the diffusion current because of the concentration, and the drift current because of the electric field. As this goes on, at some point you'll reach a steady state. They will reach an equilibrium. Drift current becomes equal to the diffusion current. So electrons are jumping, they're coming back. This is clear, everyone. Any doubts on this page? So once this keeps happening, so if you take this, so we get something like a region N type here. So this whole side has become positive. This has become negative. And we have electric field in the region. So it becomes something like a no man's land. So if an electron tries to come here, what will happen? It will get, the electric field will push you back again. If a hole tries to come here, what will happen? It will get pushed back again. So during that region, nothing can exist. There will be no electrons, there will be no holes. It is neutral region, that is. So basically you get a junction kind of thing. It's a junction between P and N. That's why we call it a PN junction. So this thing is called a forbidden gap. So electrons and holes are forbidden to enter that region. It is also called as a depletion layer. So now if you have an electric field, what will happen? Then there'll be a potential difference. So this electric field, the induced charges will create a potential difference. So if you try to plot a graph, now understand, where is electric field? Only in the forbidden gap, right? There is no electric field on the P side, there's no electric field on the N side. So the potential will be like this, and then it increases, and then it becomes again constant. This is a graph between the voltage. This gap is called a barrier potential. Means if an electron wants to jump from across the junction, you need to give this much potential. So this is the potential due to the electric field created by the surface charges. And you should remember these values. For silicon, the barrier potential is 0.7 volts. Means if you give 0.7 volts across a silicon, it becomes conducting. Exam, they won't give these values. You will need this to solve some problems. For germanium, the barrier potential will be 0.3 volts. And that's why I said germanium is a better material, but expensive. So if you make a germanium diode and a silicon diode, germanium diodes will work better. Now tell me one thing, this forbidden gap ka width, it will depend on what exactly? So we will talk about that also. So the width of the depletion layer is proportional to 1 by doping concentration. Again, what is doping? The process of introducing impurities. What is doping concentration? How many impurities did you add? That means if you have more impurities, the gap will become smaller. Another important one. And why is that? Tell me one thing. If you have a lot of electrons here, a lot of holes here, diffusion will be strong. Agreed? Diffusion will be strong. If the diffusion is strong, in order to stop strong diffusion, do you need high electric field or low electric field? High electric field. And what is electric field? Electric field is potential difference by distance between them. But here a barrier potential is constant for a given material, barrier potential is same. So how can you get high electric field? By making the distance small, isn't it? So if you have high doping concentration, then you need high electric field, means distance must be small. Are you getting the explanation for that? There. So if you have low doping, the low doping implies you need less diffusion current. So we need less electric field. And the electric field is proportional to 1 by d. Make sense? If you have high doping, you have a high concentration. So you have high electric field. Therefore, distance must be small. Is this clear, everyone? So the forbidden gap ka width will depend on what is your impurities ka concentration. The more impurities you add, the smaller the gap. Less impurities, bigger the gap. Clear with this? Any doubt so far? So there we got a p-type material and n-type material. So only p-type is useless, only n-type is useless. But when you bring them together, something interesting happens. We get a junction in the middle. It acts like a barrier for p and n to mix up. So we got a p-n junction. Clear with this thing, Adi? Ansh, Niharika? Any doubt so far? You guys should definitely go one reading through all this. Right now, everything feels like I understood. I'm pretty damn sure you'll forget in a 2 weeks or 3 weeks. So we'll be having a test anyway in next 1 or 2 weeks. And that is the reason I kept, this semiconductor logic. It's again in the end before the revision. Last week I kept these sessions again. Now, the interesting part starts from here. The forward bias. Now, how to use this? So if you take a battery, so this is our PN junction here. So if you connect a battery positive terminal to p-type, negative terminal to n-type, what will happen? The positive terminal will push the holes to the right. The negative terminal will repel the electrons to the left. So the holes and electrons are pushed towards each other. So holes and electrons are pushed towards each other. And because of that, the forbidden gap decreases. Making sense? If I give a positive voltage to p-type and negative voltage to n-type, electrons will get pushed to the left. Holes will be pushed to the right. They'll start mixing up. If your external potential becomes greater than the barrier potential, the gap will simply close and the current will start flowing. So if I give little voltage, I can make this thing like a wire. So this is the symbol for this thing. So every time who will draw this symbol, no? So We have a triangle with a line like this. This is the symbol for a diode. So the left hand side is P, this is a N. This is your new element. Till now you studied a battery, capacitor, resistor, inductor, alternating circuits ka batteries, and this is the next element, a diode. So when you see this symbol, means you understand you're working with a diode. So the important thing, when you keep this in forward bias, it becomes like a wire. Clear with this? So if you put a diode in a forward bias, it will just let the current flow. But there is a problem, remember, it will require some potential to work. So silicon diodes will eat away 0.7 volts and germanium diodes will eat away 0.3 volts. Let me show you how they'll frame a question. You'll understand. Look at this question. We got a 10-volt battery, there's a silicon diode and there's a 2 ohm resistor. Find the current. Straightforward question. Questions will be of this sort only. The first thing, whenever you do these questions, first thing you need to ask yourself is this. This is positive, this is negative. This is positive, this is negative. This is P type and this is N type. So you are giving positive to P type and minus to N type. So this is in which bias? This is in forward bias. So the holes are being pushed forward and the whole electrons are being pushed backward. So it works like a wire. So your circuit becomes like this. And in the question, it is specifically mentioned it is a silicon diode. What is the barrier potential for silicon diode? 0.7 volts. That means this diode will absorb 0.7 volts and then it will let the current flow. It's like you have to pay some tax. It will act like a wire after 0.7 volts. So silicon diode has a barrier potential of 0.7 volts. That's it. Diode is over. Then the current I will become 10 minus 0.7 by 2 plus resistance of the diode. This is where people do mistake. When people say ideal diode, they think barrier potential is 0. Ideal diode matlab resistance is 0. Since I didn't mention anything for ideal diode, R is 0. Therefore, the current in the circuit will be 9.3 by 2 amperes or 4.65. Questions will be of this sort. It will become a current electricity question once you realize what is the diode. Clear what we did? I'll give you one. You guys try this. Let's say this is a silicon diode. This is a germanium diode. This is 10 volt and this is 2 ohms. Find I. I can make it even better. Wait. Ideal diodes. You kept a silicon and germanium diode in parallel. So what is the catch here? What is silicon ka barrier potential? 0.7. Germanium ka potential? 0.3. So who will get activated first? Germanium. So silicon won't even work na. If the potential across this becomes 0.3, silicon will never get activated. Are you getting it? It is like the current has an easy way to flow through germanium. Then why will it even flow through the silicon? Since silicon ka barrier potential, it won't get activated. Remember, diode will work only if you exceed the barrier potential. So first you need to check plus, minus, plus, minus, plus, minus. Yeah, both are in forward bias. Your circuit will look like this. This guy will not even work. This is 10 volt. This is 2 ohms. This is 3 ohms. And remember, germanium will lead away 0.3 volts. So all the current will flow through germanium only. So I will be 10 minus 0.3 by 3 plus 2. 9.7 by 5. Clear with this? Did you get the logic why silicon won't work? Because I just need 0.3. Germanium will work. So potential difference across there will be something like 0.3 or something. Silicon will never get activated. Any doubts on this? So forward bias question should be like this. You just remove the barrier potential and it just becomes a wire and it becomes a current electricity equation. Any doubts on this? What happens if you keep it in reverse bias? So reverse bias is when when you keep it p-type n-type in the reverse, meaning you keep the diode and the battery like this. So this is positive, negative, positive, negative. This is p-type, this is n-type. You're giving negative terminal to the holes and the positive terminals to the electrons. What will happen? The electrons will get attracted towards the positive terminal, holes will get attracted towards the negative terminal. So both are being pulled apart. Then the forbidden gap will increase further. So if the forbidden gap increases, then it will not let current flow only. So it behaves like an open circuit. So in a reverse bias, the diode does not work only. The resistance in a reverse bias will be much, much larger than resistance in a forward bias. It has a huge resistance. It becomes like an open circuit. So far, great. But something happens. If you keep increasing the voltage, current will not flow, and then suddenly there's a huge surge of current. Something happens. The diode will just let it is like, there's a dam, you're filling with water, nothing happens. Suddenly the dam breaks and there's a big flood. Something happens like that. We will see why that happens. But in reverse bias, right, it works like a open circuit, but up to a limit. After that, it just goes off. We call this thing a breakdown voltage. So if you try to plot a graph for this, look at the graph. It's an important graph. Current versus voltage graph. If the voltage is positive, it's in forward bias. Voltage is negative, it is in reverse bias. So look at the graph. So initially in this region, up to the barrier potential, there is no current flow. The forward bias does not work. This is a barrier potential. This was a JE question. Which of the following is a graph? And there were two graphs. Most people got confused here. One graph started from here. One graph started from here. People didn't understand which graph to mark. Most people mark the red one. Answer is the black one. Just now we saw, right? There is a barrier potential, right? You have to give some potential before the current starts flowing in a forward bias. Most people, for some reason, assumed, current will, because this is what you read, forward bias is like a wire. So people will think current will flow automatically. So it's called cutoff voltage or knee voltage, or basically this is your barrier potential. So once you cross the barrier potential, current will keep increasing. Fair enough. More voltage, more current. But the reverse voltage, something happens. Initially, there is no current, zero. I'm marking in green here. Nothing happens. After a certain voltage, suddenly there's a huge surge of current. Current just rapidly increases. So why this happens? There are two reasons for this. One is called an avalanche breakdown. Again, a lot of terminology. So this avalanche breakdown happens for low doping. Again, tell me one thing, when the doping is small, what will happen to the gap? Gap will be wide, remember? Now, understand the reason. Huh? In avalanche breakdown, what happens? We have a lot of holes, fair enough. But remember, there are some electrons. On the n-type, there are a lot of electrons, but there are some holes. So when you're putting it in reverse bias, for the majority charge carriers, it is in reverse bias. Isn't it? Look at this. When you kept this minus and plus, all the electrons are pulled here, all the holes are pulled here, great. But what about this electron here? It is being pushed forward. These holes are being pushed this way, isn't it? So there are some minority charge carriers. There are few electrons and few holes. For them, it is a forward bias. Great, getting that means they're gaining kinetic energy. On top of it, you're increasing voltage continuously. What will happen? At some point, they'll gain so much kinetic energy, they will just start flying everywhere randomly. They start going in, colliding with the other bonds. They start breaking the bonds. Think of like this. There is a curfew or something, everyone is silent, right? And then you just leave 100 people on the road, and these people are burning buses and burning buildings, and they're doing all nonsense on the road. It's like these electrons, when you push them to a limit, right, they start going and breaking the bonds. And when you break bonds, more electrons are released. So there is a huge surge of current. This is like an avalanche. Ever seen an avalanche in a movie or something? Right? There's a small snow will start, and then the whole thing will just flood off. That's why we call it an avalanche breakdown. It starts small and then it's a rush. It's a common phenomenon. When you take someone or people and if you suppress them, right, initially they will not resist. Suppress them more, they'll not resist. At some point, they just go mad and said, yeah, let it go to hell. They start behaving very wildly. Happened with all of us during COVID. Maybe you guys forgot. When there's the first COVID lockdown, what happened? Everyone is in the house for almost 7-8 months. Everyone was scared, everyone was fine. Then the COVID was done. We all came out for 1 or 2 months, then COVID 2 started. There was again second lockdown, if you remember. This time, no one gave a shit. I said, let it go to hell. People were least bothered. They got so frustrated. People were eating pani puris out. People were traveling in the train. And if someone tells you COVID, they said, let it come. Yaar, abhi, ho gaya. That was a thing. So when you push people to a limit, right, that is what happened. They just give up and say, I will eat this. I will better, I die than not eating pani puri. I'll eat pani puri before I die. That is how the people have become. And if you remember, right, after that, people were traveling crazily. People are just going everywhere. Tourism and everything just bumped up. The flight tickets were expensive. It was a mess for almost a year. People even called it, revenge traveling. Because you didn't get a chance to go anywhere for 1.5 years. People took a revenge by traveling everywhere. So they had a name for that. It's called revenge traveling. So things were like that. Something like that, avalanche breakdown happens, you're increasing the voltage, you're not letting these minority carriers, go anywhere. At some point, they gain enough energy, they start going and bashing each and every bond, and everything breaks down. But unfortunately, this is a very bad thing. If this happens, this is irreversible. The circuit will literally burn down. There'll be a fire, everything will get overheated and burn down. So this is not useful for us. There is a second type of breakdown, Zener breakdown. This is important. Next class, we will see a lot of questions on this. If you have high doping, the gap will be small. If the gap is small, we get a high electric field. And do you guys remember in capacitors, if you have very high electric field, what happens to the material? There will be a dielectric breakdown. Yaad hai? That Russian hacker ka video, current passes through that pencil. So when you apply very high electric field, the region becomes conducting. And now because the region becomes conducting, the current will start flowing. This leads to high current. And luckily, this is a reversible process. If you decrease the voltage, it will become again non-conductor and current will stop. So Zener, this is the symbol for Zener diode. It's a symbol for a diode, but we have two curvy things on the top and the bottom. If you see this symbol, meaning this is a Zener diode. So the regular symbol is this. This is the diode ka symbol. But if you put two curvy things, it's a Zener diode. Means it's a diode which is made with high doping. And the best part about this, look at the graph. Did you see this graph at the breakdown voltage? After the breakdown voltage, no matter what you try to do, current will increase, but voltage will never change. So this thing gives you a very interesting property. You can use this as a voltage regulator. Means if you take a Zener diode, we will see some pretty good questions in the next class, but understand. Let's say we have a circuit. You have a variable voltage or whatever. Now you want to make sure the voltage in this, the current in this resistor must be constant. Let's say this might be your refrigerator or TV or anything. Do you want fluctuating current or a normal current in your refrigerator? The normal one. So what people do, they take a Zener diode, they keep it in parallel to the resistor. Now what will a Zener diode do? It will maintain the voltage, isn't it? Let's say this is 10 volt, means it will always maintain 10 volts. That means this voltage is also 10 volts. That means the current in this branch will be always constant. Did you guys, I don't know, I think nowadays we don't see this. When I was in school, whenever you buy a TV or a refrigerator, they also used to sell something called a voltage regulator, V-Guard karke. Ever heard about that brand? Maybe you must have seen this. On top of the refrigerator, they keep a round disc kind of thing. So what we do, right? You actually give the power supply to the V-Guard, and from the V-Guard, we give the power to the refrigerator. So if there is any voltage fluctuation in the house, refrigerator won't get spoiled. The V-Guard will take care of the fluctuation. But nowadays, all your ACs and TVs and everything will come with an inbuilt voltage regulator. So we don't have a problem now. But before, previously, that used to be a thing. V-Guard karke the brand ka name. Right? So actually kind of, that laptop ka remember, you get this big bulky thing in the middle. Seen that brick kind of thing? That also acts like a voltage regulator actually. So it will take care of the fluctuation so that the circuits don't get spoiled. So we'll talk about this more detail in the next class. Zener diode is important, but there. So Zener diode, right, can be used as a voltage regulator. There, see, we started the whole story with an electron in an atom, and then we built actually something useful, right? A Zener diode, which can be used as a voltage regulator. So more about this we'll talk in the next class. But one thing is clear: if you keep it in forward bias, current will let it flow after crossing the barrier potential. But if you put it in reverse bias, current will not flow at all. But if you exceed a certain voltage, there will be a breakdown. Now the question comes like this: how do I know there will be a breakdown or no breakdown? If you see a symbol like this, without that curvy things, it is just a regular diode, there's no breakdown. But if you see these curvy things, that should give you a big hint, boss, there's a Zener breakdown. We will see questions on that in the next class. But let's do these two. This is just simple reverse bias, simple forward bias. There's no Zener breakdown, anything. So I have taken ideal diodes, meaning resistance is 0, and I'm also assuming there's no knee voltage, meaning there's no barrier potential. Can you find the current in the circuit? So when you do this kind of questions, first thing you need to decide which is in forward, which is in reverse. Plus, minus, minus, plus, minus. This is P, N, this is P, N, meaning this is forward bias, I'll write it FB. This is reverse, I'll write it as RB. So if you draw your new circuit, remember there is no knee voltage, so I can just treat it as a 0 voltage there. This guy is gone, open circuit. Bus. Are you getting? Once you remove the diode, it becomes your regular current electricity equation. 10 volt, 3 ohms, 3 ohms. So all the current will flow through the upper diode. I will be 10/6. Clear everyone what I did? Do the B part. I'll give you a minute or two. Generally, this is the diode ka questions normally in the exam. You should just figure out whether it's a forward or reverse bias. Forward biases, you remove them, put a wire. Reverse biases, remove them. Draw the new circuit and solve. Right, Aditya. Right, Vihan. Check your calculations once. Right, Puroja. Right, Ishana. Yeah, Aditya, most of you got it. So look at this thing. So plus minus. So this is plus, this is minus, this is plus, this is minus. So that is reverse bias, that is gone. And that is forward bias, which is a wire. So it becomes a wire like this, na? This is 5 volt. This is 5 ohm. This is 5 ohm. This is 5 ohm. Won't this get shorted? ऊपर से wire हो गया ना, it becomes shorted. That 5 ohm doesn't work only. So all the current that you're giving will flow through this. So I will be 5 volt by 5 plus 5, 10 ohms, which is half ampere. Makes sense. Bus, this is the level of the questions. They don't go generally beyond this. Can I do these two also? Finish off. Last two for the day. So if you see, there are no Zener diodes, so there is no breakdown ka story here. That would be the clue. If you see a Zener diode, there will be a breakdown. We will see that in the next class. Let's finish off these two. Right, Aditya. Nere Boroja. Check again. Right, Vihan. Finish off. Get them both. I'll give you a minute. Most of you did get it. Let's see the first one. 15 nahi hai. See na. This is plus, this is minus. So this is plus minus, this is plus minus. This is P, N, this is P, this is N. That guy is gone. This guy is in reverse bias. This guy in forward bias. So if I redraw the circuit, this will be open. This will become a wire. This will be 2 ohms, which will get shorted. So 10 volt. This is 2 ohms. This guy is shorted. So all the current will flow through this shorted wire and will come back. I will be 10 by 2, 5 amperes. Got it? Now seriously, this is the level of the questions in the exam. That's what I said. Once you know what is forward, what is reverse, it is simply a current electricity equation. Can you finish with the D1 also? I gave grounded and all that stuff. So find the current in that middle branch. First of all, figure out who is reverse bias and who is forward bias. -1. Let's see. This guy is 0. This is 3. So one thing is clear. Whatever is this will be a positive voltage, isn't it? V. That is also grounded actually. This is 0. This is 5 volt. Clear? So this is in reverse bias, na? Understand one thing, people. It's not about positive and negative voltage. For example, if I give something like this, let's say this is minus 10 volt and this is minus 20 volt. Is this in forward bias or reverse bias? The voltage of P type must be greater than voltage of N type, isn't it? Minus 10 is greater than minus 20. This is in forward bias. Don't look at minus and plus signs. Higher potential, lower potential, isn't it? Voltages are always relative. So this is reverse bias. So this guy is gone. That guy won't work. And this is 4. That is 0. Perfect. This will flow. So all the current is coming from here through that battery to this. So we can read out the circuit if you want. So this is how the circuit looks. 4 volts, 3 volt, 2 ohm, 1 ohm. And this is the current. Getting how did I draw? Basically, this is grounded. This is grounded. And I can join them, isn't it? Since both are grounded, there's the same potential. I can just join them. And if you want, I can put something like this. So current will be 4 minus 3, 1 by 3 ampere. Sure with this. Any doubts on what I did? Are you clear? How did I draw the circuit? There. There is a small mistake though. Basically, when I grounded here, there is a possibility current is flowing from here. We are ignoring it. So I'll do one thing. I will say this current, let's call it I1 is 0. Now it is clear. Now I know all the current should come from here only. Current can't come from here because that is reverse bias. Clear with this? There. That's a bit about it. So the next class will be the most important thing. So till now what we did was logic gates was nice. And then so far what I created was all that materials only. So now we got a PN junction. The first application will be Zener diode. Next class we will see that. Then we'll see solar cell. Then we'll see sensors. Then we will see, rectifier. How does your adapter work? How do you get AC to DC and all that stuff? That would be the main thing. I think next first half of the class we'll wrap up the part mostly, and we will do a few more questions. And then if time permits, we'll start off with bar magnetism. That will be the next subtopic. So these chapters will go pretty fast. They're all small ones. So again, make sure to go through the entire thing, what we did today, read once. I'll also send you some reading material. Just go through that. It's around 15, 16 pages. And I'll also send you some, this 21, 22, 23 ka PYQs, which are detailed and important ones. You can do that. Or you can do your PYQs from whatever book you're doing. That is also fine. Again, like I'm saying, these chapters, if you do PYQs, it is sufficient. So preferably try to do it within 2 to 3 days of teaching. Don't take too much time. 4 minus 3 is 1 by 3, right? Wait, what you're saying? So you're saying this is grounded, na 0. And then I think I need not give this. You're right, Purvaja. I can solve without giving that current actually. I can even ask you that question also. What is the current flowing through that? So this is the current now. This is also 0. So if you apply Kirchhoff's law from this branch, you'll get what is 0 minus I into 1 minus 3 volt is equal to 0. Right. That's what you're saying, no? 1 by 3. Sahi hai. That means the current coming from here, this will be some I dash. That also I can calculate. So I dash will be 4 by 2, which is 2 ampere.
No, sir. In the initial diagram, can't we just say that across the resistor, the current will be delta V by R?
That only, no? This is 0, that is 0. I did the same thing. Now you can do that directly. I drew it unnecessarily. But okay.
But then
You're saying even without the reverse bias, huh? You're saying.
But then if any current is going through that.
You are right. I shouldn't have drawn that ground actually. Are we better, huh? Now it is better, I guess. I should have removed that. That thing was unnecessarily. I know what you're saying. Even if I had diode or no diode, the answer would have been same. If I had grounded there.
No, sir, but wouldn't it open the no resistor wala wire because it is shorted, sort of?
Yeah, I'm saying that only. If I remove the ground, if I remove this, now what do you think? Now that won't be 0, na?
Right.
I shouldn't have grounded that point. That was a mistake. यहाँ पे ground नहीं लगना चाहिए था. Now it will be fine. ठीक है? ठीक है. With that, we'll wrap up for the day. So I'll see you guys on Friday. We'll continue from here. Again, finish your modern physics of pending work and start doing semiconductors also. Not much. At least do some 10-15 questions and read the notes. That is sufficient. You will remember. Okay, with that, we'll wrap up for the day. So any doubts, anything else, stay back. I'll see you on Friday, same time. So take care, stay safe.